All right, good morning, good afternoon, good evening. Whenever you're listening to this video, it is I, Dr. Kaz, and I am doing my second review video for Chapter 2. This is an optional video. There's no required assignment that comes with this, but I try to do one for each chapter just to kind of break things up a little bit, just to remind you your primary source of information should be coming from the textbook. All right, whether you have a hard copy of it or if you have it the ebook, which is on the Connect website. That's your primary source. Then the soft chalk lessons, when you go into Blackboard and you go and look over some of the written material there, that is a primary, secondary resource. And then these review videos are just some topics that I like to discuss with you, the students, in which some students in the past have had difficulty understanding certain concepts, but just to kind of better to nail down and cement in some of the basics of this material. So that being said, I hope everybody had, for those of you that are in the United States, had a nice Labor Day weekend. And for those of you that aren't, I still hope you had a wonderful weekend. Let's start off here talking about Chapter 2. It's a little bit of biochemistry. Just to let you folks know, I don't want you to be too concerned about my background in chemistry. I tell this to all the classes. I feel like full disclosure is important, but I failed chemistry in high school. But not to worry, because when I took it again in summer school, I passed it with a B. And then in college, I got straight A's. I even took biochemistry. And I've even taken organic chemistry and some biochemistry courses. So I've taken a decent amount of courses in chemistry or some sort of related field. I'm more of a physics person. I love physics, believe it or not, even though I teach biology courses. But just understand that this topic of chemistry that we'll be covering in this chapter will not be too in-depth. It's only the stuff that you'll need to understand and know to help you to further understand our course, anatomy and physiology. A lot of physiological processes are based on chemical reactions and the properties of chemicals or elements, okay? So that being said, there's a couple things you want to understand. First of all, matter, okay? The definition of matter is a material or substance that occupies space and it has mass. And some people like to think of it as weight, all right? But that is what matter is, all right? It has two properties to it. One, it has mass. And two, it occupies space, which means it also has volume. All right, so there's three forms of matter. We see it in our body. You have the solid, liquid, and gas. And the examples are given there. Solid in the form of bone and cartilage. Liquid in the form of blood. All right, gas in the form of any of our respiratory gases like carbon dioxide, oxygen. Okay, so all three states of matter exist in our bodies. So in Chapter 1, you may recall reading that there's certain levels of organization to an organism. And in this course, we start with the smallest, and that's going to be the atom. Okay? So an atom, I'm going to read the definition here for you. The atom is the smallest particle exhibiting chemical properties of an element. An element would be, we have the known elements of our universe. And that's going to be when you hear someone say nitrogen, or sodium, or oxygen, gold, silver. Those are all elements, okay? And so an atom has all the properties of that element. So there are 92 naturally occurring elements that make up matter, and we organize it into what we call the periodic table of elements. I do not have a picture in this slideshow. You don't really need to, for this slideshow, you don't really need to know it, but refer to it in your textbook if you want to learn more about it, okay? So, whoops, my computer's going a little bit slow. Let me go back one. There we go. All right. So another item that you want to learn is a structure called an ion, okay? Basically, an ion is a charged particle. So when you have these atoms, okay, and you add an electron to an atom or you take away an electron to an atom, okay, you're going to wind up with a charged particle. So the atom will either be positive or negative. At this point, I'm assuming that you all have learned what an atom consists of. Think of it as our universe. You have the sun at the center of the universe, and you have the planets orbiting around the sun. Well, an atom is very similar. At the center of the atom, you have a nucleus. And inside that nucleus, you have two subatomic particles. One is a neutron. Neutrons are neutral. They carry no charge, but they do have mass. The other subatomic particle that's inside the nucleus is the proton. P proton, P positive. The protons are positively charged subatomic particles. So surrounding the nucleus, like the planets surround the sun, you have the electrons, and they orbit around. All right. Now, without getting into too much detail about it, all right, we're going to use the shell model. For those of you that have taken organic chemistry, I know we have the cloud model, but for this, I'm going to use the shell model. All right. Makes it easier to understand. All right. But you have the electrons that orbit around, and they carry the negative charge, and they are very, very small subatomic particles, and they virtually have no mass. Okay. But for every proton, you should have an electron. Okay. And that would make the overall atom neutral. What that means is if you have, all right, two protons in the nucleus, then you should have two protons orbiting around the nucleus. Okay. Now, what will happen is when we get an ion, we'll either gain an electron. So say you have two protons orbiting, two protons in the nucleus, and you have two electrons that normally orbit the nucleus. Then we add a third, all right, that's orbiting the nucleus. Then we added a negative charge to that. And so that atom now has a -1 charge. Two protons, two positive charges, three electrons, three negative charges. Okay? And that gives us a negative charge of 1 because we have one more electron than we do a proton. So let's flip that. Okay? You have two protons in the nucleus, two electrons orbiting. Now we lose one of those electrons that are orbiting. So now we have two positive charges and one negative charge. So the overall charge of that atom will be a +1. And that will give us an ion. Those are charged particles, an atom with a positive or negative charge. And that will happen when we lose or when we gain one or more electrons. Okay? So we're going to find out throughout this course, right, that these ions have significant, very significant physiological functions. Okay? Potassium is one. It's an electrolyte. We also call it an electrolyte. And we add it into our sports drink. All right. So in some cases, it's great because when we add it to the sports drink, it helps to replenish the lost potassium that we lost in our sweat, because potassium is very important for neurological function, for our nerves to properly conduct nervous signals, all right, which allow our heart to beat. Okay. And that is also why we use, all right, potassium, okay, for lethal injections. Too much potassium can cause, all right, I'll say almost instantaneous death. All right, it will literally stop the heart. Okay, so sometimes we want to take two or more atoms and we want to stick them together and we want to hold them together, much like a welder might hold together two pieces of metal. Well, when we hold two or more atoms together, we create a bond. And the first type of bond I want to talk to you about is a bond. Okay? So an ionic bond is when we have cations, and just in case you don't know what a cation is a positive ion. All right? You have more positive charges than negative charges. So that means that atom lost electrons. Okay, because when you're losing electrons, you're losing negative charges and you'll have more positive charges. And I think of cats as furry and cuddly, and they're positive to be around. All right, you want to snuggle them if that's your thing. All right, so those are cations. Anions are the opposite. Those are the negatively charged ions, which means they've gained electrons. So they have more electrons than protons, so you have more negative charges than positive charges. So as you've probably heard the saying, opposites attract. So negative and positive charges will be attracted to one another, okay? And so when we create these bonds, all right, this attractive force, we call it electrostatic forces, okay? And that's what forms table salt, all right? Our salts are formed like that. So table salt, you can see the molecular formula here, sodium chloride, all right? So that means we have a sodium ion, and we also have our chlorine ion, okay? I'm going to show you a picture of this, all right? So let's just read through it here, and I'll show you a picture. All right, so the sodium atom, all right, has one electron in its outer shell. By the way, the outer shell is called the valence shell. You need to know that, and I'll show you a picture here in a moment, okay? The valence shell is called the outer shell, or vice versa. The outer shell is called the valence shell. And your atoms always want to fill that valence shell, all right? So an atom always wants to have its outer shell to be filled. And the maximum number of electrons in the outer shell, the valence shell, is 8, okay? And so there's a principle. We call it the octet rule, all right? And that's the atoms wanting, all right, to have that valence shell be full. So it's either going to try to fill it with electrons, or if there's only 1 or 2 electrons, or maybe 3 electrons in the outer shell, it might get rid of all 3 of those all 3 of those electrons, dissolving that shell, and then it'll go to the next shell that's underneath it. And that should be full, because you fill the shells, and once you fill the inner shells, you start with the inner shell most, and you fill that up with electrons. Once that gets full, and we're still adding electrons to our atom, then we start another shell. And when that one gets full, then we start another one. But we always fill the inner shells first. So if we're starting to shed electrons or donate electrons, we'll always do it from the outer shell, all right? And then we work our way in. So that's one way that an atom can have its valence shell full, if it starts to shed off some of the outer electrons in its outer shell until it has a full valence shell. And I'll show you a picture, okay? All right, so sodium has 1 electron in its outer shell. So it's going to want to lose that electron, okay? And it's going to donate that electron over to chlorine atom, okay? Because chlorine has 7 electrons in its valence shell. So all it needs is 1 more electron to fill that up. And when it does that, all right, when it fills it up, then it's full and it's completed or satisfied the octet rule. All right, so let me show you a picture here. Picture's way better. All right. So here you can see, here's sodium, all right, and the chemical symbol for sodium is Na. You need to know that. You need to memorize that. Na is sodium, and it comes from the Greek word for sodium, which I can't remember right now. Cl is chlorine, okay? K is potassium. Fe is iron. I'm just throwing a couple out there. You're going to need to know these. So if you look at sodium, oh, one other thing too, before I forget. The inner shell, the very first shell. So here's our nucleus. Then we have our first orbital or shell here. All right, and you notice there's only 2 electrons in it. That is another rule that you need to know. That the first shell, the maximum number of electrons that it can hold is 2. Okay? So the first shell is always 2, is the most that it can hold. Here's your valence shell. This is the outermost shell. That one will be 8. Okay? All right. So you notice that the second shell has 8 electrons in it. Okay, so it's filled that shell, so it added another shell. And in sodium, it just has 1. Chlorine, all right, on the other hand, has 7 in its valence shell. So you're probably thinking, it's much easier for chlorine to gain 1 more electron than to shed all 7. That's a lot more work, okay? And vice versa for sodium, all right? It's much easier for sodium to just give up its 1 electron in its valence shell than to try to gain 7 more, okay? So sodium's nice enough where it donates an electron to chlorine, okay? So it lost its one of negatively charged electrons. So now sodium has +1. If you don't see a number in front of the plus sign here, it's always to be 1. So if we were to count up all the electrons, you got 2 in the first shell, 8 in the outer shell, that's 11 electrons. We have 11 protons. So this has a positive charge of 1. And we write it like that. Okay? Chloride, in the meantime, has gained an electron. So it's filled up its valence shell. So if we count all the electrons, you got 2 in the inner shell, 8 in the next 2 shells. All right? That is going to be, let's do math. Wait, did I say that correctly? 2 in the inner shell. All right? And then we have 16, 17, 18 electrons altogether. We have 1 more negative charge than positive charge, so we have a negatively charged ion. So we write chloride as Cl negative. So this is negatively charged. This atom is positively charged. Opposites attract. They move towards each other, and they form what we call a lattice crystal structure. And that's the form that we give salt. And that's what happens with ionic charges. Okay, ionic bonds. All right, so the other type of bond that we're going to talk about are covalent bonds. Covalent bonds share electrons. They don't donate, but they share. So I call covalent bonds the kindergarten bonds because sharing is caring. I learned how to do that in kindergarten. So covalently bonded molecules will share, all right, electrons between 2 or more different elements. Okay? So we give a name to that. We call those I can't talk today. Molecular compounds. Carbon dioxide is an example because we have 2 or more, all right, different elements. Carbon is C, O is 2, all right, it is oxygen. Now, molecular oxygen, it's not different elements, okay? So that's not a molecular compound, right? So carbon dioxide. So when you see this letter format here, all right, this is called the molecular formula, and it's basically the ingredients of what we're talking about. The molecular formula tells you what's in it's a recipe of what's in our molecule. C is carbon, but there's no number following it, so it's always understood to be 1. If O is oxygen, if you see a number after it, it's telling you how many oxygen molecules there are. So we know there's 1 carbon molecule because there's no number after it, so it's understood to be 1, and then oxygen has a 2 following it, so that means there's 2 oxygen, okay? All right, so again, covalent bonds share electrons, okay? And this happens when both of the elements or atoms, all right, or not both, or if there's 3 or more, okay, it's when those atoms need electrons. So they're not willing, all right, to actually donate or to gain an electron, okay, that will just share them. So we'll usually see this, all right, when we're dealing with atoms that have 4 to 7 electrons in their outer shell. And if you look below there, all right, you can see those elements there, hydrogen, oxygen, nitrogen, and carbon, which are very common elements. All right, when we're dealing with the human body, with organic systems, All right. And so all of those four elements form covalent bonds. Okay. So what does a covalent bond look like? Let's take a peek. All right, here you can see here's a hydrogen atom. It's got one electron in its shell. It only has one shell. One proton in the nucleus, one electron in the in its outer shell, its only shell. Okay. So remember, the first shell can accommodate 2 electrons at the most. So one hydrogen atom meets up with another hydrogen atom, and then they start to share both the electrons. So they both satisfied, all right, filling up that shell. Okay. Remember, nature wants balance. It always wants to be stable. So what it's done is now is it's gained that electron, okay? And so now it has a full shell. Carbon has 4, all right, electrons in its valence shell. Okay, those are represented by the blue. So it wants to get 4 more electrons there. So it can do it in a variety of ways. This example is showing you it's just acquired 4 hydrogens because they also want to fill up their shell. So it gets 4 hydrogen. Now you count 8 altogether for carbon's valence shell, but also each hydrogen has satisfied filling up its shell with 2 because that's all it can have. So this is kind of what water, another example. Okay, you can see the same thing. Oxygen has 2, all right, 6 electrons in its valence shell. So it just needs 2 more. So it goes around, it picks up 2 hydrogen. So they're all satisfying, all right, filling up that valence shell, that octet rule. All right, so that's that for kind of the basics of chemistry, some understanding. We're going to continue on, but we're going to start to talk about acids and bases. That's an important concept that you're going to want to know. And in Bio 211, when you get into renal physiology and acid-base balance in our bodies, you're going to want to learn, going back, and this is a principle from chapter 1, the set point number that your body wants to keep. It has a certain normal range that it wants to keep certain physiological functions in, like your body temperature. Number 98.6 is the normal set point body value, but it ranges from a high of 99.1 to a low of 96.4, and that's the normal range. Well, your blood pH, same thing. There's a range for that. And the normal value, the set point is 7.4, but it fluctuates between 7.35 and 7.45, right? So we're going to learn a little bit about acids and bases. So I'm going to start off here with water, all right? It is what we refer to as a neutral solvent. I don't know about you, but when I do dishes, sometimes I have to soak a pot or two or some baking pans, and I used to soak it with, yes, some soap, but sometimes just with water, because water is a solvent. It's a great solvent. It helps to break things apart. Part of that is because of this property here. That water, the molecular formula for water is H2O. It's written down here. All right. Will spontaneously dissociate to form ions. What does that mean? Dissociation is when H2O, our water, simply, come down here to the bottom of the page here, simply will just break apart. Okay? And it'll break apart or dissociate into what we call a hydrogen ion, so H plus, and a hydroxide ion, OH. All right, one's positively charged, one's negatively charged. And it breaks apart into equal parts. Okay? Equal parts. All right, so this will just randomly happen in water. And in fact, you want the statistic, it's 1 out of 10 million ions per liter of water. This will happen. Okay? So the bonds between the oxygen and the hydrogen just break apart, and it forms equal parts of hydrogen ions, the H plus, and equal parts of the hydroxide ions, the OH negative. Okay? So this is important, and this is why water always remains neutral. And I'll talk to you about what neutral means in a moment. Okay? You can see it at a grander scale with this formula here. Let me get rid of all those lines there. All right. You can see it a little bit more. See, so here's two water molecules. All right. So you'll see one of these water molecules will do this. Okay. And so you've got this second water molecule here in our equation. Come on now. Okay. So you see this water molecule will break apart and yield this. Okay. And then what will happen is that we have our second water molecule. Well, this hydrogen ion will attach onto that water molecule, giving us this. That's called hydronium. Okay. And then from the first water molecule, we'll yield that. Point being is we will always have equal numbers of positive hydrogen ions and negative hydroxyl ions. That's the point. All right, you need to understand that concept. So when water disassociates, it'll always give us equal numbers, all right, of the positive hydrogen ions and the negative hydroxyl ions. That's why one positive and one negative, they cancel each other out. So they'll always be neutral. That's why water is always neutral. So I include this first molecular formula here, all right, because people wonder what happens when there's two or more, all right, water molecules. Is there any type of interaction? Yes, there is, okay? But don't worry, you're not going to be really responsible for knowing that, but you will be responsible for knowing that, okay? All right. So let's talk about what an acid is. And you want to write this down and make sure that you understand this. An acid, all right, when it disassociates, when it breaks apart spontaneously, it's always going to produce a hydrogen ion, okay, and an anion, which is a negatively charged, all right, ion. So another name for the hydrogen ion, all right, is, and again, I didn't come up with this, is a proton. Okay, I know earlier we talked about a proton being a subatomic particle that lives inside the nucleus. I get that. Yes, I know. All right, but also when we're dealing with acids and bases, a proton is a hydrogen ion. Okay, this right here, that is a proton. Okay, so when you take an acid, all right, and you dump it into a beaker of water, the acid will disassociate. It'll break apart. All right. So what an acid will do is it will always increase the concentration of free hydrogen ions. All right. So we'll use an example here, right, of hydrochloric acid, HCl. Okay. So when hydrochloric acid breaks down, I'm going to try to write this out. It's hard using a mouse. HCl. Okay, so now we dump that into water, and this is what happens. It busts apart into hydrogen ion or protons, and into an anion, and in this case, that's chloride. Okay, so keep that in mind. So when we take an acid and we dump it into water, it'll bust apart, okay, or disassociate, and we get a lot of these floating around in that water. Okay, a lot of those. So that's what I'm talking about here with this statement. Increases the concentration of free hydrogen ions. Because you keep pouring more hydrochloric acid into the water, you're going to keep breaking the hydrochloric acid apart, and it's going to yield us a lot of the hydrogen ions, or these protons. Okay? So, the stronger the acid, the more dissociation we'll get of the hydrogen ions. So stronger acids will dissociate much easier, It'll happen a lot. So hydrochloric acid, which was what we find in our stomach, all right, has a pH value of 1, okay? It will break apart easily. Weaker acids, we will get much less dissociation, okay? We'll talk more about carbonic acid, all right, in Bio 211, all right, but it helps to buffer our blood, helps to maintain the pH balance in the blood, okay? So here's that generalized formula, substance A, an acid, all right? I gave you the example up here, all right, which would be hydrochloric acid is going to yield a hydrogen ion here and our anion, which was the hydrochloric acid, okay? So we refer to acids as proton donors because they're always giving up whenever you add it to water. All right, acids will donate those free hydrogen ions, those protons, into the solution. Okay. All right. So let's talk about the other guy, the base. All right. So make sure that you write this down. A base accepts hydrogen ions when it's added to a solution. So I think of a base, all right, as a Pac-Man, and it goes around and it goes and gobbles up hydrogen ions. Okay, that's what it does. So we give it a name. Those hydrogen ions are also called protons. So it's a proton acceptor. So think of a base like a sponge for hydrogen ions, or a sponge for protons. Go around and they absorb them. Okay. So when you add this to a solution, it's going to decrease the concentration of those free hydrogen ions that are floating around a solution. So say you've got a beaker of water, you add the hydrochloric acid into it, and it disassociates. Now you have all these free hydrogen ions floating around. Well, now I want to soak them up and get rid of them. So I'll add a base into that. I'll add like ammonia or bleach. And those guys will go around, all right, and they'll absorb those hydrogen ions. So hence, the more absorption we get of those hydrogen ions, the stronger the bases, all right? Less absorption, weaker the bases. That's why ammonia and bleach make such great cleaning agents, because of this principle, okay? Now, weak bases have their place, don't get me wrong. All right, bicarbonate, again, you'll learn about this in 211, is another base, the weak base that floats around in our blood and helps to maintain that pH balance in our blood, okay? All right, so an important concept is on this next slide here. So you need to understand the difference between acids and bases. Very, very, muy important, okay? All right, look at the top of the slide there. It talks about pH neutralization and the action of buffers. That's what we're going to start talking about here. All right, so what is pH? Okay, pH is a scale that we use to measure, all right, if something's acidic, basic, or neutral. Okay, so the pH scale ranges from 0 to 14. And what it does is it tells us the relative amount of the hydrogen ions in the solution of whatever we're measuring. Like a pool, they're always checking the acid, the pH balance in a pool because they have to maintain a certain level, all right, according to DHEC. Okay, so if you go to a community pool, the lifeguards are always checking it every hour or whatever they're supposed to. Okay, they're checking to see what the pH value is. If it's high, all right, means it's too basic, and so we have to add, all right, something that's acidic to drop that pH value down. And if it's very low, all right, it means it's too acidic, and we need to add a base. So start off with this concept here. The pH value of plain water is 7. 7 is right in the middle of our scale there. Remember, our scale goes from 0 to 14. And in the middle of it is 7. Remember what I said earlier. Water is neutral, okay? It is neutral. So the value of 7 is, say it with me, neutral. Okay? So 7 is neutral. It means it's not acidic and it's not basic. I'm going to try to write this out. Because remember what I told you going back to that first slide on this topic here. H2O, when it disassociates, it disassociates into one hydrogen ion and one hydroxide ion. All right, but in equal parts. Remember what I said? You have one negative charge something and one positive charge something, they cancel each other out, and that's what happens. So when water disassociates, all right, so that 1 in every 10 million water molecules breaks apart, all right, per liter, okay, it'll give us equal parts of hydrogen positively charged ions and equal parts negatively charged hydroxide ions. So that's why it's neutral, okay? You need to know that, okay? All right, so keep in mind what pH is, okay? It's a measurement of the relative amount of hydrogen ions in a solution, okay? So this next part is crucially important. You need to star this, all right? Know this, memorize it. pH and hydrogen ion concentration are inversely related. So what the heck does that mean? Simple. One increases, the other one has to decrease. Okay? So if one decreases, the other one increases, vice versa. So if you want to get all scientific on it, it's going to be the inverse log, all right, for a given hydrogen ion concentration. But if you want to be simple like me, all right, as your hydrogen ion concentration increases, your pH value will decrease. And vice versa. As the hydrogen ion concentration decreases, my pH value will increase. Okay? And I'll show you what all that means. Keep in mind that the pH and the hydrogen ion concentration are inversely related. It's crucial that you know this. Inverse. One goes up, the other one comes down, and vice versa. Okay, so let's figure out what the heck I was just talking about. So when we're talking about the pH scale, which is 0 to 14, okay, if we have a solution that has equal concentrations of hydrogen and hydroxide ions, the one that you really want to pay attention to is this right here, okay? But if we have equal concentrations, somewhat like what happens with water, okay, it'll be neutral. All right, for every positive, there's a negative, and they cancel each other out. So that is neutral, and we assign that a value of 7 on the pH scale. Okay? Follow me on this. If not, when you're watching this, pause it, rewind it, and listen to this again. Okay? All right. Now, we have a solution that has more or greater amounts of the hydrogen ion concentration than the hydroxide concentration, all right? Then that means we are going to be dealing with something that's acidic, and it will have a pH value of less, that's what the symbol means, less than 7. So acids have a low pH value. Okay, a low pH value. pH value 1, 2, 3, 4, 5, 6, 6.7, all right, 5.9. Those are all going to be acidic substances because they have a greater concentration of hydrogen ions or the protons compared to the hydroxide. Okay? Because remember what we said, going back to the previous slide here, all right, where are we? Boom. As the hydrogen ion concentration increases, pH value decreases. That's our inverse relationship between the two. All right, so conversely, when we're dealing with, all right, a solution that has greater amounts of hydroxide ions and less amounts of hydrogen ions, all right, we are dealing with a basic or alkaline solution. And they'll have a pH value greater than 7. That's what this symbol means. Greater than 7. Okay? So going back to the previous slide here, as our hydrogen ion concentration decreases, the pH value will increase. Okay? All right. Make sure that you commit that to memory. You got this. I know you do. All right. So when we're talking about moving from a pH value, all right, of 7 to 6, all right, we go from 5 to 4. All right, you just want to know this is kind of, I don't want to say an FYI, but when we move from one increment to the next, that's a tenfold change. What does that mean? So for the example listed down there, we go from a pH value of 6, all right, it has 10 times a greater concentration of hydrogen ions than pure water, because pure water is 7. So when we go from neutral, okay, and then we go down to 6, that's a tenfold or a 10 times greater concentration of hydrogen ions. And then if we go to 5, if we move from 6 to 5, it's 10 times greater concentration, all right, from 6 to 5. Okay, so it's just a tenfold change. That's what we're talking about there. All right, so this picture here says a lot. All right, so first of all, it discusses, here's our pH value. Okay, so we have 0 value and we have 14. At the middle here is 7, that's pure water. Okay, that's neutral. It means we have equal parts of hydrogen ions with hydroxide ions. Okay, so if we look at our picture here, as we start to decrease in the pH value, all right, the lower numbers, you'll start to see we're increasing our hydroxide ion concentration compared to the hydroxide ions. So you can see in our beaker here, we have a lot of hydrogen ions floating around the solution. Remember what we said, all right? The more the hydrogen ion concentration, the more acidic something will be. So you can see our pH value is decreasing. You can see here are some acids, hydrochloric acid, all right, produced in your stomach. When it's mixed around with other stuff in your stomach, it gives our stomach acid a pH of 2 or 3. Okay, that's pretty acidic. It could burn a hole through several structures. Pretty much the desks that you sit at school could burn a hole through that. Okay, so conversely, when we go from neutral, 7, down to these higher values, 10, 11, 12, you can see our beaker here, we're seeing fewer and fewer hydrogen ions. Okay, so when we see less hydrogen ions compared to the hydroxide ion concentration, so decreasing hydrogen ion concentrations, increasing pH value, we're getting to our more basic solutions. All right, antacids, you take those, all right, when you have an upset stomach, your stomach acid secretion is increased, all right, and you want to decrease it, you take an antacid that'll help to decrease the amount of stomach acid you're producing. Ammonia, bleach, all right, all these are bases. So you might want to take a peek at this to make sure that you have a pretty decent understanding. So I'm teaching you all this why. Why do I need to know this? Well, there's physiological chemical processes that occur in your body, okay? And it brings me to this. 2 important concepts that you want to understand. Neutralization, all right, and buffers, okay? So neutralization is what happens when the problem has already occurred, okay? When you have a solution that has become too acidic or too basic, and we need to get, all right, our pH back to neutral, okay? So it's quite simple, all right? When you have something that's too acidic, you simply add a base to it, okay? And it returns it back to neutral. Much like I said on the previous slide about stomach acids, all right? When you need to neutralize stomach acid, you'll take antacids like Tums, all right, and they have a high base content, and that will neutralize the acid, and vice versa. If you have a solution somewhere in your body that's too basic, then we'll add an acid to it, because our goal is to always get back to pH value of 7. Okay, neutralization. All right, so neutralization often occurs when we've already changed the pH. So now with buffering, that concept is when we're trying to prevent the change of a pH. We don't want the pH value to change, so we're going to try to prevent it. All right, so if we start to add too much of an acid to whatever, or too much of a base to whatever, in order to try to prevent the change of pH, okay, we'll start to see that our body has certain components that will prevent, all right, the changing of the pH. For example, if your blood starts to become too acidic, your kidneys will start to excrete, all right, hydrogen ions in your urine. Okay. So buffers are going to act either to accept hydrogen ions or to donate hydrogen ions. All right. So if they accept the hydrogen ions if there's too much acid, all right, or they'll donate hydrogen ions if there's too much of a base going on. Okay. Because we want to always keep our blood pH in this range right here, 7.35 to 7.45, usually around 7.4. Okay, slightly basic. If you get too acidic, what will happen is you can get what's known as denaturization, and that's when proteins start to break down. You don't want that. Considerable amount of your body is made up of proteins. Your proteins start to break down, you're in trouble. All right, a lot of physiological processes can go haywire and malfunction, and you don't want that. All right, let's get out of that chemistry and we're going to end up with a couple more slides here and start to break into biological macromolecules. Okay, almost done. Okay, biological macromolecules are going to be, macro means big. All right, these are the larger components that you're going to be learning about all semester, and you'll even carry it into 211. All right, you've heard of things called carbohydrates, fats or lipids, proteins, nucleic acids. Those are macromolecules. So we're going to talk about these macromolecules for a second. Okay, first of all, you need to know they're large organic molecules. And when we say organic, that means they will definitely always contain carbon, but not only carbon, all right, hydrogen and oxygen. Okay, they have to contain those, especially carbon. Carbon, if you don't have carbon, you're not considered organic. That's a chemist definition of organic versus not inorganic. Okay. Some macromolecules will have nitrogen, phosphorus, or sulfur too, but they always have to contain carbon, hydrogen, and oxygen. Okay. All right. So these carbon skeletons will contain what we call hydrocarbons. And what a hydrocarbon is, if you look at the name, it tells you exactly what's in it. It only will have carbon and hydrogen atoms. That's it. Hence, hydrocarbons. All right. Some of these will also have what we call functional groups. And these functional groups give some of these macromolecules their specific type of characteristics. Okay. So some of these functional groups, all right, are going to be polar. And what I mean by polar doesn't mean positive or negative, all right? It just means that it gives it a distinct end to the molecule, okay? So these functional groups, most of them are going to be polar, and they're also going to be able to bond with hydrogen or create a hydrogen bond, okay? So some of these functional groups will act as acids, and others can act like bases. And they'll have these terms on the end of them, a carboxyl group or an amine group. So if you're reading in there and you're looking at, especially when we get into the amino acids, you'll have a carboxyl group and an amine group when we're discussing amino acids, all right? And it helps to give them some of their functional characteristics. All right, so let's talk about the first type of macromolecule, and that's lipids, all right? Fats. First characteristic you need to know about these guys is that they're water insoluble, which means when you add them to water, they will not dissolve into the water. You need to know that, and you've probably seen that. For those of you who've ever made pasta and you're boiling the water and you take olive oil or whatever type of oil you like to put into the boiling pot and you pour it in there, you'll notice that the oil kind of floats on top. All right, it doesn't immediately just disappear or dissolve. All right, that's because it's water insoluble. All right. The next important characteristic you need to know about lipids is that they're stored energy. I won't get into the whole thing about the energy storage, but basically, when we were hunter-gatherers, we didn't know when our next meal was coming from. So your body learned how to, whatever you ate, it would not waste it. It's very frugal. And so it would store the excess energy that you got from your diet, and it would convert it into lipids and store it as fat. Okay, because way back when we were a nomadic people, we travel around a lot. Okay, so you'll store lipids, it's stored energy. Okay, when we get into chapter 4, for those of you that have already gotten there, you know what I'm talking about. The plasma membrane, that's the outer envelope of the cell. All right, considerable amount of the makeup of the plasma membrane are lipids, specifically called phospholipids. All right, and then finally, the chemical messengers in our body. All right, remember our nervous system uses electrical current to send nerve signals. All right, but our body also likes to use chemicals. All right, those are referred to as hormones. Okay, so there's 4 types of lipids you want to know, all 4: the triglycerides, the phospholipids, that's the cell membrane, steroids. All right, that's part of our hormones. All right, and the eicosanoids, those are locally acting hormones, all right, like prostaglandins, prostacyclins, thromboxanes, all right? Those are all involved, all right, in chemical messaging, especially in the inflammation pathway. You'll learn more about eicosanoids in not chapter, I can't remember the chapter off the top of my head, but it's in Bio 211. So I say a lot of that, in case you haven't noticed. Oh, you'll learn about it in Bio 211. Well, you will. So that's why I'm not going into detail on it. I'm just trying to give you the base foundation there. Plus, I don't want to make this video 3 hours long, okay? All right, the next type of macromolecule are carbohydrates. An interesting characteristic of carbohydrates is that you will see a hydrogen atom and an OH, all right, group are always attached to every single carbon. Okay? So the chemical formula for carbohydrates is going to be CH2O with N on the outside there. The N represents the number of carbons in the atom. So if we have 6, all right, we put the 6 here where the N is, and that means we have 6 hydrogen. Excuse me, I can't think today. No. If we have 6 here, that means we'll have 6 carbon, 12 hydrogen, and 6 oxygen. What you would do is just take the 6 here and multiply it by each number that's behind a letter. Remember, there's no number there. It's implied that it's a 1. So 6 times 1 is 6. So that means you'd have 6 carbon. 6 times 2 is 12. That means you'd have 12 hydrogen. 6 times 1 for oxygen would be 6. So C6H12O6. Okay? That's just a generic way of telling what the chemical formula is of the carbohydrates. So when we discuss carbohydrates, we've got our monosaccharides, which are simple sugars. You saw those earlier in chapter 2 when you talked about glucose, galactose, fructose. All right. Then when we take 2 monosaccharides and attach them to one another, we get a disaccharide. Okay. And then when we string along a whole bunch of monosaccharides, then we get what's called a polysaccharide. All right. And those are many monosaccharides. Okay. So the basic carbohydrate that you want to know, and you need to know this structure, is glucose. When I say you need to know this structure, you need to know this molecule. Okay, glucose, 6-carbon carbohydrate. It's a ring structure. All right, it looks like a hexagon. You've probably seen it in the book. That's an octagon. 1, 2, 3, 4, 5, 6, 7, 8. Yep, sorry, too many. I gotta learn my geometric shapes. Don't do that one. Okay. All right. So this is the most common monosaccharide, and it's the primary nutrient for energy to the cells. What's that mean? What that means is your brain loves glucose. And your brain is like the whiny cry organ in your body. It gets top-notch billing for everything because if the brain goes, so does the rest of the body. All right. There's a saying out there amongst a lot of exercise physiology people. When I mean that, I'm not talking about actual exercise physiologists, but people that study exercise physiology, like weight trainers. I'm only as good as my central nervous system, and that's true. Okay, so if your brain is not functioning right, a lot of your body functions will be way below par. All right, so your brain gets top billing. It always is going to be the first to get glucose. All right, so that's why your body's always monitoring and keeping your blood glucose levels at a specific level. All right, because it needs to satisfy the needs of your central nervous system. All right, amongst other tissues too. All right, so glucose will always be monitored and it's always going to be carefully maintained in your blood sugar levels. Okay, but now sometimes you want to save glucose because once you've satisfied all the cell's energy requirements, what happens with the leftover glucose? What do? Do you pee it out? I hope not, because then you'd have sugar in your urine and that would be a problem. All right. You're going to save it for a rainy day. All right. So you're going to store it, and you're going to store it in the form of glycogen. All right. And there's only two organs in your body that do this. Your liver is one of them, and your skeletal muscle is the other. Okay. So when you have excess glucose floating around in your blood, all right, and all the other tissues are full, they're like, hey, we're good for now. All right, no problem. Your skeletal muscles will start to accumulate glycogen inside the cell, all right, in the cytoplasm, which is actually called the sarcoplasm in skeletal muscles. And your liver will do the same thing. Okay, and it'll bind these glucose molecules together, and it just starts to string them along, and it makes a long chain of them. All right, it'll make a polysaccharide, and glycogen is a polysaccharide. In the process, all right, of these glucose monomers getting stuck together is called glycogenolysis. And if you dissect the word, all right, genesis is to create, all right, to make. And so what are we making? We're making glycogen. So we put the first couple of letters of glycogen on the title of this. So glycogenesis, to make glycogen. Okay? Now, you're in a situation in which, hey, I need some of that stored glycogen. It's 3 in the morning, you're asleep, and your body still has to run its metabolic processes. Okay, no problem. I am now going to, with those long glycogen chains, all right, I'm going to start to cleave off, all right, some glucose molecules off of those glycogen chains. So that process is called glycogenolysis. To lyse means to break down. Okay, what are we breaking down? Glycogen. All right, so we just start to cleave off those monomers, all right, through the chemical process is called hydrolyzation. Okay, and as we chop off those individual glucose molecules, they go into the blood and float around to whatever tissue needs them. Now, there are situations in which you want to make glycogen, but you don't have glucose to make glycogen. Say you only have proteins or fats, no problem. We've got a process for that, and that's called gluconeogenesis. All right, so genesis, we already know what that means. Neo means new. All right, so we're going to make a new source of glucose, all right, from a non-carbohydrate source, fats and proteins. So the liver does that. So you can see how important it is for your liver. This slide here, I'm going to give you a second to look this over while I go fill up my coffee, all right? Because this one here shows you all the functions of proteins. Give me 1 second. I was a radio host, that would be bad. That would have been dead air, and that's a no-no. But I'm not. Okay, so proteins. You can see all the functions here of proteins, and you're going to learn a lot of those this semester and some next semester. I won't get into every single one of them, but next semester you'll get into a ton about enzyme activity. And an enzyme is a catalyst, much like a lighter is a catalyst to start a fire. Okay, well, some chemical reaction in your body, you need a little bit of help. So proteins will act as an enzyme, that catalyst to start. You're hearing a lot in the news in the past several months about antibodies. Well, guess what antibodies are? They're proteins, okay? And they're used in defense, immune defense. All right, we'll learn in chapter 4 about the transport functions of proteins, how they allow things to move inside of cells and also in and out of cells. All right, also about how to create support systems inside of a cell, because a cell, much like our body, has a skeleton. We call it a cytoskeleton. They help with that. All right, they will also help with the movement of certain tissues. Perfect example, skeletal muscle. In chapter 10, you will learn about this sliding filament theory and how certain proteins slide past one another during a muscle contraction. All right, and then in regulation and storage, we'll learn more about all that. I didn't want to get into too much detail on that. Again, I don't want this slideshow to be 3 hours long. All right, so let's talk about the general protein structure. All right, so much like glycogen, all right, it has monomers that make up its structure. Okay, well, our proteins have monomers, the building blocks. Okay, and the building blocks of proteins are what we call amino acids. All right, we have 20 different amino acids that are found inside of our living organisms, and they're referred to as essential and non-essential. Some your body can make, and some it cannot, and it has to get through the diet. Okay, but these proteins will have on each end of them, all right, and these amino acids will have on each end of them functional groups, and we'll have an amine group and a carboxyl group. And this kind of goes to that point earlier on in the slideshow here a couple slides ago, that part of that group will act like an acid and the other one will act like a base. Point being is that it's polar. Okay, you have a polar end, meaning you have an amine group on one end and a carboxyl group on the other. Okay, but what they'll do is they'll covalently bond to, all right, another amino acid. So let's say this. An amine group from one amino acid will then covalently bond to a carboxyl group of another amino acid. All right, and they'll start to build a chain. Okay, all right, so keep that in mind. All right, that's it for proteins. And now we'll finish up here with nucleic acids. All right, nucleic acids are going to be these molecules that are going to do two things. They're going to either store our genetic information, all right, and they can transfer that genetic information. Okay, our DNA and our RNA. All right, remember, inside of our cells, we have our genome, and that's the blueprint for everything that makes us us. And so there's two classes involved. All right, we have the deoxyribonucleic acid, which is DNA. And then we have the ribonucleic acid, which is RNA. A couple characteristics you want to know about these. Deoxyribonucleic acid, or DNA, is double-stranded. Okay, ribonucleic acid is single-stranded. All right, where do we find DNA? All right, it's going to be found in our chromosomes. Where are those found? In the nucleus, and you even have some in the mitochondria. If you don't know what that is, we'll talk about it in chapter 4. It's the powerhouse of the cell. Okay, ribonucleic acid is also found inside the nucleus, but then it's also found in the cytoplasm of the cell. If you don't know what that is, don't worry, we'll talk about that in chapter 4. That's the slime or the goo that sits outside the nucleus, which is the control center of a cell, but inside the plasma membrane. All right, we're not going to be discussing DNA and RNA significantly in this course. That's in chapter 3. You're not responsible for chapter 3, but if you do want to look it over, feel free. All right, but make sure that you know everything else, okay? If you were to take a genetics course, you will learn about it in much more detail. This isn't a genetics course, okay? All right, so the big nucleic acid that's going to be very important for you to know in this course is this guy right here, adenosine triphosphate, ATP. Okay? This molecule, and you want to make a huge note of this, this molecule is involved in the chemical energy transfer within cells. What the heck does that mean? It's the energy currency of the cell. Okay? It's the energy currency. This molecule will allow certain processes to occur in your body. Pretty much any process in a cell that requires energy will use ATP. Okay? An important concept that you want to know is this right here. Covalent bonds between the last two phosphate groups, okay? Because basically, and I didn't include the picture here, all right, when we talk about the breakdown of ATP, it's a nucleotide, which is the adenosine here, all right? But then it has two nitrogenous bases, the adenine. Don't worry about that, all right? This is the important part. 3 phosphate groups. Okay, so that's where the T comes from, triphosphate, right? Each of those bonds between the phosphates are energy-rich bonds, okay? So when you require energy for some sort of chemical reaction to occur in your body, you snap off, all right? You snap one of those bonds, okay? So when we have 3 phosphates and we need some energy, we're just going to snap off the last phosphate, all right? And that bond, all right, between the last phosphate and the second phosphate, when we snap that off, energy gets released. And we use that energy for whatever chemical process that we need. So we go from having 3 phosphates to 2 phosphates. And we call that new molecule ADP, all right, which stands for adenosine diphosphate. Okay? So that's essentially where we get, and that's that whole process. Right, it's just snapping that chemical bond between the last phosphate and the second phosphate, and it releases energy for whatever we need. These 2 substances here, NAD and FAD, again, they help in creating, all right, ATP. All right, and you'll get into that, what they're necessary for in 211 when you learn about metabolisms of the cells. You'll kind of visit all this information again. I know you thought you escaped it, but you don't. All right, you'll hit it again in 211. But this is what happens when you start to form. You'll need these 2, all right, nucleotides here to form, all right, ATP, and that occurs in the mitochondria in the electron transport chain. All right, I'm going to stop here. That's the end of chapter 2. All right, we will get into chapter 4 on the next video. And I'm not sure that hopefully I should have that posted before the Blackboard Collaborate session on Sunday at 7 p.m. on September 13th. All right, that's Sunday at 7 p.m. September 13th. If you cannot make it to that, you need to send me an email telling me why. All right, so I can send you a link for that email, for the video. All right, I hope you learned something. If you have questions, of course, always email me. All righty, have a great day, and I'll see you in the next video.